All right, guys. Can you guys hear me? Can you guys hear me?
Yes.
All right, perfect. So let's get started. So welcome, guys. So you're actually in the 2022 AMC12-AIME Bootcamp, lecture number 1. Lecture number 1, we basically make it as an open lecture. So all the students, they can participate, they can understand what's going to happen in this 2022 AMC12. So before we get started, we want to give you guys a quick background. So in order to help you guys basically prepare for the upcoming AMC12 and AMC10, we basically created 2 boot camps. Today, we're going to focus on the AMC12, and for the upcoming Monday, we're going to focus on the AMC10. So basically, we're going to give you guys like 10 lectures, try to cover as much as possible for most the important part for the upcoming AMC10, AMC12 math competition. So here is like a quick syllabus, what we're going to be covering for our 10 lectures, especially for today's lecture, AMC12. So we're going to use like 3 lectures talking about the geometry part. So as you know that generally we're talking about the 2D geometry, which is the most important part for all the kind of North American math competition, not only AMC, but also all the Euclid related exams. So this is extremely important. And also, we're going to use our second lecture talking about the 3D geometry. But generally speaking, in our North American math competition, most of the 3D geometry problems, they can be converted into a 2D geometry. We're not using like the real 3D geometry. You might see some other exams all over the country. However, we're going to focus on the 2D part. Using the 2D part and 3D part, doing the conversion. So most of the 3D problems would be converted into a 2D problem. Okay, and also in our lecture number 3, we're going to go to our coordinate geometry, which is also a very important part for the geometry, right? And also, you know that for the coordinate geometry, it's kind of like liaison between like the real geometry and also the algebra, right? The focus of doing the coordinate geometry is trying to use the algebra methodology, use the equations, using different coordinates, so on and so forth, and try to resolve some kind of the coordinate, some kind of like the 2D geometry problem. So that's kind of like a liaison between the geometry and also the algebra. Okay. And starting from our lecture number 4, we're going to talk about our algebra part. Because algebra is always the most complex part. I won't say it's complicated, but it's a little bit complex because we have like so many concepts. We know algebra from day 1, right? So that being said, there are like so many different concepts, different things all over the places. We like to use 3 lectures to cover them as much as possible. We're going to cover some functions, equations, inequalities. These are more like the calculation, proof, so on and so forth. And then for the second part, we're going to use our technologies we introduced to investigate the sequence and series. We're going to investigate the exponents and the logarithm, especially logarithm. This is reserved for AMC12. Right? In AMC10, you barely learn anything about algorithm, right? But AMC12, this is more kind of popular. And for our lecture Algebra 3, we're going to talk about the trigonometry, complex number. Complex number is especially for AMC12, and some complicated polynomial-related concepts, right? And then moving forward, we go to our third part, which is the counting and probabilities. So counting and probabilities in nature, they're pretty much the same thing. But there are some focus for these 2 categories. So therefore, we give 2 lectures. One focus on the counting principles, while the other one focus on the probabilities. And then the last but not least is the number theory. Number theory is kind of like the most challenging, most unfamiliar concepts, especially for our North American students, because if you go to our regular school, we barely talk something about the number theories. Especially for AMC, there are certain theorems, certain properties. They're actually, you have to learn it before you can go to the math competition. If you really have no idea what is the concept, what is the kind of like the theorems, it will be very challenging for you to handle the AMC related problems. So that being said, in our last 2 lectures, we're going to be focused more on this number theory topic, try to give you guys as much possible this kind of theorems, strategies, tricks here and there. So this is basically how I organize our 10 lectures. And one of the most important thing is that for our lecture, we do not really focus on simple problems. I know some lectures, they just give you like the real problem papers, one after another. I find it's kind of like a low efficient because even though you do like a medium problem, there might be a medium plus one problem. You still get confused. So this is more like a fish and fishing, right? So in our lecture, we actually focus on the fishing part. In our each lecture, we're going to break it into three major parts. So for section number one, it's always going to be some concepts. We're going to use some time, 1/3 of a lecture, talking about the most important concepts, theorems, properties, so on and so forth, that you need to remember in order to go to a certain part. For instance, today, we're going to focus on the 2D geometry. We're going to start over with all those kind of basic background concepts, and that's going to help you to understand what will be covered, what will not be covered in the math competition. Second part is, we're going to give you some kind of like summary, the most important type of questions. Okay? So there are millions of questions for certain topic, but we like to classify them into certain categories. So knowing the category, so you can just do 1 or 2 example representatives, then you'll be understandable about how this entire part works. So we're gonna help you guys to classify all the important types of questions for this certain category. And then the third part, we're gonna give you the real questions or the real problems. We're going to take the problems from the AMC12 and some of the problem from AIME. We just try to give you guys a combination. I know this is kind of the AMC12 bootcamp, but we still want to give you guys a little bit like AIME problem, help you to expand your horizon. If you only focus on AMC12, these days the complexity is getting bigger and bigger. Every day, every time the complexity, like the exam paper, is a little bit more complicated than the previous year. So sometimes if you only focus on the AMC12, it might not be kind of like efficient enough. So therefore, we actually organize our lecture with a little bit like AIME problem, kind of help you guys to expand your horizon, and then you will be understandable how this entire thing works, right? So this is kind of like a basic short and brief introduction, how our lecture works. And our lecture has a lot of interactions. If you have any questions during the lecture, let me know. You can type it in the group chat, or you can unmute yourself, ask a question. Because today is actually open lecture. We might have like more students than we used to have. So it's up to you. You can either talk to me or you can chat with me. So as long as we can make sure kind of like an order of our entire lecture is good enough. All right, I think that's pretty much what I want to say as a quick warm-up. If all good, let's fly to our lecture number 1. Today's open course, we're going to focus on the 2D geometry. All right, so let's get started. 2D geometry, lecture number 1, 2D geometry. Like I said, before we jump to all the problems, let's try to do a quick summary. What are the most important concepts that you need to know in order to cover this 2D geometry related part in the upcoming AMC12 math competition? Well, the first one, we're going to go to the triangle inequality. Okay, triangle, this is kind of like a foundation, right? For all this kind of 2D geometry stuff. Even though you see like the quadrilateral, you see polygon, all those kind of complicated shapes, they will be converted into a triangle before you get started all your calculation and your proving strategy. So having a good understanding for the triangle is always important for the entire 2D geometry. For the triangle, I think the most important, the most basic stuff you learn from day 1 is kind of the triangle's inequality for the 3 different sizes, right? The sum of 2 sizes will be greater than the third one. That's kind of like the basic foundation for a triangle. And sometimes a student say, hey, Alex, we still learn another thing. You basically give me 3 add, right? 3 sum. Also, we learn something like A minus B should be lesser than C, A minus C lesser than B, B minus C lesser than A, right? We basically learn 2 sets. One is adding them together. The other one is actually doing a subtraction. However, if you have a quick observation, you'll be find out, you see, this one is exactly A is lesser than B plus C, right? Which can actually be converted into here. And the same thing applies. This guy is A lesser than B plus C, right? It's also be converted into here. So that being said, even though you have 2 sets of inequalities, but they're not really independent. All these kind of subtraction related things, they can be converted into the sum related formula. So that being said, whenever you try to remember the formula, you can just basically forget about this part. Only focus on the sum related formulas. These three formulas will be good enough. They will cover all the scenarios that you will have to know for the math competition. All right. And actually, this guy has the vector form as well, right? You can see x vector plus y vector. This total magnitude is actually lesser or equal to x magnitude plus y's magnitude, right? This is actually the vector form. If you put it into here, right? This is x, this is y, this is your x plus y. So these are two forms help you guys to remember how this inequality works for this triangle. Okay, so this is actually, I think, the #1 important inequality for the triangle. And there's actually another very important inequality in the triangle I think people will understand. If I just give you any kind of triangle, this is like theta, then I'll be able to see sine theta, if I take the absolute value, will be less or equal to 1, greater than 0. And the cosine theta will be greater or equal to 1, greater or equal to 0, greater or equal to 0. Let me change this, right? So this is going to be 0 less than 1, right? So as long as you have any kind of triangle, it can be whatever type of triangle, you have another very important, or we can say an intrinsic relationship within the triangle, right? So this is also very important. So this looks like very trivial, but trust me, sometimes this very trivial property can really give you guys a very good direction for you guys to, create an inequality and then taking from there, solve the problem. Later, I'm going to show you some problems from AIME, and they're actually using such a simple strategy. Okay? Second theorem, Pythagorean theorem. Oh, Pythagorean theorem is basically you learn from elementary school, right? It's like so important and so basic. If you have a right triangle, so therefore, this guy square plus this guy square is actually equals to hypotenuse square. Well, to be honest, in most of the time, the North American math competition will not really give you a right triangle and let you guys to do some Pythagorean calculation, so on and so forth, because that's kind of like a too naive, right? Actually, in the reality, what's going to happen is that the question is going to give you a bunch of sizes for triangle, okay? So the triangle might have different kinds of things here and there, whatever. And then during the calculation process, you will automatically calculate the length of here, the length of here, the length of here. Okay, so these must be calculated during your calculation process. And what a coincidence. As long as you calculate the three sizes of this triangle, A, B, C, you can happily find out these are actually the three sizes of a right triangle. So that being said, we give a name, this is the Pythagorean triple. So what I'm trying to say is that they won't directly tell you, okay, this is a right triangle, please help to go ahead doing the calculation. Well, alternatively, the question is going to give you the three sizes of a triangle, and then let you decide this is actually a right triangle. And taking from there, you might be able to do a lot of calculations and solve the problem from there. Okay, this is actually more like a reverse engineering you're going to be seeing in the math competition. So I actually did some quick analysis. So we did some, research for the last 20 years. So these are all the numbers they have ever tested you in the last 20 years. 3, 4, 5, of course, right? 5, 12, 13, 7, 24, 5, 5, 15, 7, and the other one is 20, 21, 29. So these are the 5 very popular triangle, I'll say the Pythagorean triples that has been tested in the North American math competition. So you know what? There's only like the big data analysis tells us this. And there's no guarantee in the future they're still going to test exactly the same Pythagorean triple. But my suggestion is that at least a couple of these Pythagorean triples, have like a rough idea. That's going to be very helpful as long as you go to the math competition, because it always give you a direction. Okay, this might be the direction I can find out a right triangle and taking from there, solve the problem. All right. So that's the second. Let's go to the third one, angle bisector theorem. Angle bisector theorem, it speaks for itself, right? You have a triangle and you have an angle bisector. AD is the angle bisector of angle A. So of course, whenever you have the angle bisector, you know angle 1 equals to angle 2, right? So this is kind of like given. But trust me, based on our analysis, we barely use this, two angles are the same. They're not very important, to be honest. And most of the time, as long as you see the angle bisector, they're going to test you the angle bisector theorem. So that being said, the relationship between the sides are way more important than the relationship between the angles. If we take this as an example, you'll be able to see as long as you have AD is an angle bisector, then automatically you have BD over DC is actually equals to AB over AC, right? This is the basic property of the angle bisector theorem. Trust me, this is extremely important. I can't say 100%, but almost 95%. As long as you see the problem give you an angle bisector, 95%. The question is going to test you the angle bisector theorem. Like I said, angles are the same, not that much important, but angle bisector is extremely important. Okay, bear in mind, this is going to help you a lot in your math competition. Okay, the other one is the famous Stewart theorem. What is like a Stewart theorem? Stewart theorem is actually an intrinsic theorem for a triangle. So this is actually, what kind of triangle? Not necessarily a certain type, any kind of triangle. As long as you have a triangle ABC, you have a dynamic point D on the BC side. You make a connection. Now, in this triangle, you have 1, 2, 3, 4, 5. 5 segments, right? And then automatically, you can find out there's a relationship between these 5 segments. And the relationship is here. M times A times N plus D times A times D equals to B times M plus times B plus C and C. So this is actually kind of like a very important property. It reveals the basic property for any triangle. So now you have an equation. This equation have 5 variables, right? So that being said, as long as you know 4 variables, you will be able to calculate the last variable. And the last variable is uniquely identified by such an equation, which is very interesting, right? Because there's nothing really special for the triangle, but you can have such a fixed relationship between all the segments. Okay, so how to remember this? So we have a shortcut. You can remember a man and his dad put a bomb in the sink. A man and his dad put a bomb in the sink. Okay, so this is actually something very important. Okay, so that's going to help you to review an intrinsic relationship for any kind of triangle you will basically see. Where does A come from? A? A is here. This is A. Yeah, right. This is A. M plus N equals A. Okay, good question. So, some student is going to say, you know what? I really can't remember. This is like too complicated. I have to remember so many things. But if you can't remember this, there are 3 important certain scenarios I think you need to remember. So because generally speaking, Stewart is actually for any kind of triangles. But now let's try to make a little bit specific for our condition. If I make the condition a little bit stronger, let's say whenever AD is an angle bisector, AD is not a random segment, it's an angle bisector. If that's the case, what's going to happen? You're going to have the famous angle bisector length theorem, because AD is the angle bisector. Angle bisector length theorem is going to be AD squared equals to AB times AC minus BD times DC. Okay, this is actually whenever AD is a specific angle bisector. Then what about the second case? Whenever AD is the median of BC side, what's going to happen? That's actually the famous median length theorem. So 4AD squared is going to be equals to 2AB squared plus 2AC squared minus BC squared. Okay, that's going to help you to determine what is the length of a certain median given in a triangle. And the third specific scenario is, in that case, AD is no longer a specific thing. However, AB is equal to AC. You're looking at an isosceles triangle. In that case, you're going to have AD squared equals to AB squared minus BD times DC. Okay, just like I said, if you can remember the intrinsic form of this still word, that's going to help you do everything. But if you can't, it doesn't matter. At least you might be able to know those three specific scenarios with a stronger condition. AD is an angle bisector, it's a median, or it's isosceles, so on and so forth. That's going to help you to determine the length of certain segments. All right. So moving forward, number 5, the properties of the centroid of a triangle. You know, as long as you got a triangle, so the triangle has different centers, right? You might have the in center, you might have the in center, you might have the circumcenter, right? You might have the centroid, you might have the orthocenter, you might even have more, right? There are different kinds of centers all over the places. And among all of them, actually the most important is the famous centroid, which is the intersection of 3 medians. Trust me, this is actually something so important because AMC love to test you. What are the most important properties where you're looking at the centroid? There are something I have already listed out for you. The first one is that the centroid actually cut the 3 medians into 2-to-1 relationship, right? So let's say I have a median. I'm going to give name, maybe this is D, for instance. So this G point is going to cut your AD into 2-to-1 relationship. Same thing applies if this is F. CF is also a median. So this G point is going to cut your CF also into 2-to-1 relationship. Same thing applies for the other median. This is very important. It has nothing to do with the shape of the triangle. It works for everything. Okay? You know what? If you know such a property, you can easily solve the 2018 AMC12B question number 13. If you know this, that's going to help you to solve the problem in about 5 seconds. If you don't, that's going to take a lot of time for you to do the calculation. Okay. All right. So the next one is for this specific centroid. If we go to our coordinate geometry, we can actually find out a very important thing. If I know the coordinates of your A, B, C, there are x1, y1, x2, y2, x3, y3. So the coordinate of the centroid will be just 3x coordinate, adding them together, divided by 3, 3y coordinates, adding them together, divided by 3. It's actually a very easy peasy way for you to remember. So from time to time, that's going to help you a lot in order to calculate, what is the coordinate in a specific centroid, so on and so forth. So try to remember this. That's going to save you a lot of time in some certain problems. All right, this is our number 5 property. Now let's go to our number 6 property. We're talking about 2D geometry. Of course, congruency, or to be more specific, congruent triangle is something so important. So you need to know some basic rules how to determine the triangle's congruency, right? So basically we have 3 sizes, right? If 3 sizes of 2 triangles that are equal to each other, of course, these 2 triangles is going to be congruent to each other. Or side, angle, side. 2 sizes and also this included angle. Same thing, 2 angles included the side, right? And 2 angles and the opposite angle, the opposite side of one of the angle, which is here. right? So these are actually something so easy, right? I think you guys already know that from day one. I just take this opportunity to give you guys a quick summary without going to the super details. And for our right triangles, it's a little bit special because right triangles, you have this Pythagorean theorem. As long as you have two right triangles, the hypotenuse are the same, and also one of the legs are the same. Because we have the Pythagorean theorem, automatically the third one will be the same as well, right? So you do not really need to know the third one. You can just basically say HL, right? The hypotenuse and also the leg, they're the same. Automatically, you have these two right triangles are actually congruent to each other. Well, there's a tiny thing I want to highlight is that why we do not have the SSA, two sizes and also an opposite angle of a certain side. So in our case, let's say we have, this is 6, this is 11, right? And we have, this is the angle 30. Because the reason is that in order to make sure you have 11 here, 30 here, 6 here, you might be able to create two triangles. They both have the 6 as the third side. Let's say one is here, one is here, right? You can make sure this is actually isosceles triangle. So these two triangles, they both have the third size equals to 6. Well, of course, these two triangles, they're not the same, right? So that's the reason why you can't have the SSA, right? And besides this, all the other determination rules are very popular in order to determine two triangles that are congruent to each other. So a very quick observation you can find out, in order to make sure two triangles that are congruent to each other, you can have different kinds of determination rules. However, nevertheless, you must have a side information, right? You must have a side information in order to make sure these two triangles, they are congruent to each other. Okay, that's our congruency. To be honest, congruency is very rarely seen in the North American math competition. Why? Because, to make sure two triangles that are congruent to each other, they must be exactly the same. This is kind of a very strong condition, right? You won't be able to have like two triangles that are always exactly the same. So that being said, congruency is not really popular in a math competition. Well, alternatively, if you can't find two triangles are exactly the same, it is quite possible you'll find two triangles that are proportional to each other. They look quite alike, but they're not exactly the same size. In our case, that is the similar triangle, aka similarities, right? Similarity is way more important compared to the congruency. And in the North American math competition, you're going to see the similar triangles all over the places. So same thing, how can we determine two triangles that are similar to each other? You can have two angles. As long as two angles are the same, these two triangles will be similar to each other. Side, angle, side. As long as you have two sizes and the corresponding, the two sizes, and also this included angles are the same. So therefore, you're going to have these two triangles similar to each other. Same thing, side, side, side. The three sizes, they're basically proportional to each other. Of course, you're going to be able to see the two triangles, they are similar to each other, right? You see, to determine two triangles that are similar to each other is actually more flexible. As long as you have two angle information or you have two side information, you'll be good, right? You'll be able to determine two triangles that are actually similar to each other. Just like I said, you won't be able to see too many congruent problems, but you definitely see a lot of similar triangle problems. In our regular lecture, we actually introduced there are 10 different types how to determine two triangles that are similar to each other. So you need to basically remember all those 10 different prototypes, take it as a conditional react. In our lecture, we're going to keep saying this, conditional react. If everything you need to think from the very beginning, you're doomed. You won't be able to finish that. You won't be able to finish that much problems in the AMC exam because the time is too limited. But if you have a lot of conditional react, you kind of like very mechanically find out the solution for different problems. That's going to help you a lot in order to do a lot of problems. Okay, in our lecture, we're going to be teaching you guys or giving you guys a quick recall. What are the conditional react we keep talking about in our different sessions? All right, so let's continue. Number 8, Menelaus. So I gotta say number 8 and number 9, these two theorems, okay, they're more like for AIME, okay? You barely see a lot in the AMC12 exam, but it's more like a favorite for AIME. AIME really like to use these two theorems. That's going to help you to solve a lot of relatively complicated geometry-related stuff. So what is the Menelaus? The Menelaus means you have a triangle ABC. Let's say you have a triangle ABC, and there is actually a transversal line cut the triangle two sizes at one point and another point. One is P, one is R, and also it intersects the extension of the third side, okay, extension of the third side at point Q. As long as you have this, you're going to have such a relationship. BP, CP, CQ, QA, AR, RP. So these 6 segments, right? If you do this ratio between the 2 segments from the same side and then multiple the 3 different ratios together, that one is going to give you 1. Again, this is like an intrinsic property. It has nothing to do with the shape of the triangle. It works for everything. That's more like our Stewart theorem. It works for all the triangles and help you guys to get an intrinsic relationship for all the triangles. Okay? Well, after the Menelaus, we always go to the Sivas. The Sivas theorem is also the same thing. You have any kind of triangle, you have a dynamic point X in the middle of triangle. It does not have to be any center, just basically any point of, okay? And then you make 3 lines, make an extension. Basically, you're going to extend and try to intersect with the other side. Then as long as you have this, you have BD over DC, CE over EA, AF over FB. Exactly the same thing, right? The ratio for the 3 parts, multiple them together, equals to 1. So the Menelaus theorem and also the Sivas theorem is more like a twin brother. They're talking about something similar, very kind of a generic intrinsic property for any kind of triangles and works for everyone. Having such a relationship is always going to help you to create an equation and take them from there, solve the problem. Okay, try to remember this. Number 10, let's go to the famous sine law, cosine law. As long as you know a triangle, you have 3 sizes, automatically you have the sine law, right? A over sine A, B over sine B, C over sine C equals 2R. R is the radius of the circumcircle, right? R is the radius of the circumcircle. This is the famous sine law. And the other one is the cosine law. Cosine law is a little bit more complicated, but you know, basically, you will be able to determine cosine C simply by using the 3 sizes. As long as you got a triangle, you have 3 sizes, there's no angle information, only is the size information. You can determine a side, that you can determine the angle of a triangle simply using the side information. Trust me, this is actually something very interesting, right? You're going to be really using such an interesting property, try to determine the angle measurement fairly quick. And trust me, this is an extremely important property because AMC12-AIME, they love to test it. You know what? This theorem is actually tested so many times. Every single math competition, they're going to test it several times, not only one time, several times. So having a good understanding for the cosine law is going to be extremely helpful for you to do all those kind of math competitions. Please bear in mind. Okay? So I think this is pretty much what I want to say for this triangle part. Okay? And in the future, as long as you see quadrilateral or even you see polygon, okay, more complicated shapes, it doesn't matter. All those kind of complicated quadrilateral or polygon problems, they can all be converted into triangle problems. So that being said, as long as you're dealing with some complicated shapes, always cut them into triangle. Triangle is the prototype, is the foundation for this entire 2D geometry. Any kind of like polygon, complicated stuff, always convert it into a triangle problem that's going to help you to solve the problem very quick. Bear in mind, okay? If you go for a direction, you always deal with polygon, you might go for a wrong direction. You have to stop and think about it. Can I convert it into a triangle and solve the problem using triangles property? Okay. After talking about the triangle, we're going to talk about our circle, right? Circle is actually very important, right? In the math competition, you're going to see a lot of complicated problem comes from circle, not from triangle. But no problem. Circle is also an application for different triangles, put them together, and you're still going to use the triangle property to solve the circle-related problems. So talking about a circle, first one, always the first one, power of a point, right? Power of a point is not only one theorem, it's actually a series of theorems. It contains 3 series. The first one is the chord theorem. As long as you got a circle, you have 2 chords intersecting together, automatically you're going to have DE times EB equals to AE times EC, right? This guy, right? There's 2 chords cut each other, and you can multiply the 2 pieces together. They're equal to each other. Second part is tangent secant theorem. As long as you got a circle, you got a point which is outside the circle, you want to make a tangent and then make a secant. Automatically, you're going to have AB squared equals to BC times BD. Okay, this is extremely important. And the third one is more like the secant theorem. The second theorem is that you get a point which is outside the circle. You want to make 2 secants. So you're going to have BC times AC equals to CD times CE. This times this times this, right? These are actually something quite understandable, right, for this. So here, before we move forward, we like to give you guys a quick summary. You know, as long as you see a tangent, there might be a tangent, a line tangent to a circle, or 2 circles tangent to each other, right? As long as you see a tangent, what are you going to do? What are the conditional react as long as you see tangent? Okay, this is something extremely important. As long as you see a line tangent to a circle, you're going to make an auxiliary line from the center of the circle to the tangent foot, right? Connection between the center of the circle to the tangent foot, because automatically you're going to have a perpendicular 90 degrees. Is that right? Which is extremely important. As long as this is actually our case number 1. Our case number 2, as long as you see 2 circles that are tangent to each other. Okay, could be here. Could be here, external tangent or internal tangent. Automatically, you're going to do the connection between 2 circle centers. Do the connection between 2 circle centers. Because as long as you do the connection between 2 circle centers, if 2 circles that are here externally tangent, this line, this point, and your tangent foot, they will collinear, right? Collinear. And for this guy, okay, if you make an extension, the 2 circle center and this tangent point is also collinear, right? It's also collinear. And another very important thing is that if I want to make a common tangent line here, a common tangent line to these 2 circles, this is going to be 90 degrees. Is that right? 90 degrees. The common tangent line for these two circles will be definitely perpendicular to the extension, to the connection of these two circle centers, right? These are two very important properties. Okay? And there's another one which is even more important, is something like this. As long as you have two circles that are externally tangent to each other, and you have a common tangent, basically cut these two circles, not in the middle, it's actually outside, right? In that case, there's an extremely important shape you need to remember. First thing first, always do a connection, right? Connection, connection. This is going to give you two perpendicular lines, right? And also, like I said, always connect two circle centers, right? As long as you did this, I'm going to teach you the third one. From the relatively smaller circle, you want to make a perpendicular line to the radius of the big circle. So here, this little triangle is actually something very interesting. Let's have a quick look at it. So let's say I call this as like a big R, okay? This is big R. This is like smaller r, right? So this is going to be big R. This is going to be smaller r. What is this? Because this is a small r. So basically, this is going to be what? This is also could be kind of small r, right? It's a rectangle, right? So here, you're going to have big R minus small r, which is very understandable, right? So that being said, in this little red triangle, I'm going to drag it out from here. This is your big R minus small r. This is your big R plus small r. So you can automatically determine the length of this third side. The length of the third side, which is under root big R times small r, right? Trust me, this is like so easy, right? But sometimes that's going to help you a lot in some relatively confusing, complicated problem. So that being said, as long as you see two circles, they're externally tangent, and you have a common tangent line, always think about this little triangle here, because you will be able to determine the three sizes for this triangle. This is very, very important. Trust me, later you're going to find out how important it is. It's going to help you to do a lot of crazy problems. Okay? So let's go to the other very important property, which is the quadrilateral, the cyclic quadrilateral. You know what? If you have a quadrilateral, the 4 points, they're all in the same circle, right? We'll be able to say this quadrilateral is a cyclic quadrilateral. So what are the important properties of having a cyclic quadrilateral? So generally speaking, there are some side-related information and some angle-related information. So the first one I got to say is the angle information is the opposite two angles. They're actually supplementary to each other, right? So the two green plus the two red, they are both equals to 180 degrees. This is the property of a cyclic quadrilateral, and vice versa, right? Whenever you have like a quadrilateral, you have such a relationship. So this quadrilateral is going to be a cyclic. Second part is more like this. If you want to basically see here, ABD, I'm going to change a different color. Angle ABD, this guy, is actually equal to angle ACD. As long as they're facing the same chord, so these two angles are actually equal to each other, right? I think this is actually a very easy peasy property. As long as two angles facing to the same chord, they actually have the same measurement. Same thing for the second one. I'll give another example. BCA, this angle is the same as BDA, this angle, because they're both facing the same chord, right? So this is actually a very important property for most of the cyclic quadrilateral. Well, the next one is pretty much the area of a cyclic quadrilateral. So as long as I give you a quadrilateral, I give you three sizes. I mean, I give you four sizes. Quadrilateral have four sizes. normally speaking, you won't be able to know the size, right? However, if this is a cyclic quadrilateral, you will be able to determine the side right away by using such a formula. See, this one is more like the Heron's formula, right? Not exactly the same, but quite similar, right? So this is actually kind of giving away how to rapidly determine the area of a cyclic quadrilateral. You do not have to break it into different triangles. You can just directly do the calculation using the four sizes right away. So far, so good? All right, so let's continue. The other one is, again, for the cyclic quadrilateral, that's the famous Ptolemy theorem, right? As long as you got a quadrilateral, which is like the cyclic, then automatically you have such a relationship. The products of these two diagonals, AC times BD, actually equals to what? The sum of the product of the opposite two sizes. CD times AB, CD times AB, that's the color, I think I need to use the color green, right? So these two sizes, multiply them together, and BC and AD, these two green side, you multiply them together, that's going to give you a very important way how to basically determine these two guys plus these two guys actually equals to the product of these two diagonals. This is actually a very important property for the cyclic quadrilateral. And also, you can use such a property to determine a cyclic quadrilateral. If I have a quadrilateral, it just basically have such a relationship, right? This guy times this guy plus this guy times this guy equals to this guy times this guy, the two diagonals, that you can claim, okay, this is going to be a cyclic quadrilateral. So most of the properties from a cyclic quadrilateral to this property, or using the property, you can directly apply to determine a cyclic quadrilateral. This is our necessary and sufficient condition. All right, so trust me, this is actually something very important. All right, so moving forward, we're going to do a quick summary how to determine the area of a triangle. So trust me, this one is actually very important. Our analysis indicates in our last 20 years, there are 70% of the geometry problem that are somewhat using this area of a triangle. Maybe not directly calculate the area, but kind of ask you to determine the area in the middle of the calculation and moving forward, help you to solve some problems. So having a good understanding for how to determine the area of a triangle is actually extremely important. So let's have a look at it. How are we going to determine the area of a triangle? First thing first, this is the definition, right? Definition is like so easy. You know the bottom, you know the height, you'll be able to determine the triangle's area. Don't forget, you need to divide it too. Second one is our famous Heron's formula, right? Heron's formula actually give you a methodology. As long as you got a triangle, you have three sizes, then you'll be able to determine the side, determine the area of this triangle simply by using the three sizes. There's no need for you to determine the height and then, basically do some calculations, so on and so forth. Heron's formula is going to help you to do the calculation simply using this. Okay, so normally speaking, if you plug in the value, you're going to see such a form. And if you do some simplification, you can see this is actually a final form. Okay, how you can directly use it. There's no need for you to do the S from here as an intermediate variable. You can directly jump from here all the way to here. This is like the final way was the way for you to determine the area of a triangle using three sizes. If you don't remember this, you can always get started from here. Okay, so this is actually something quite understandable. Well, here, I want to give you a quick side talk is that, sometimes if the question gives you the three sizes of a triangle, for instance, give you three, I don't know, 5 something, just give an example, okay? In that case, I think there's very easy, you can directly using the Heron's formula. However, if sometimes they give you some weird numbers, under root 3, under root, I don't know, 3, yeah, maybe under root 5, under root 7, for instance. So if that's the case, okay, of course you can still using the Heron's formula, but in that case, you're going to do the first thing is under root 3 plus under root 5 plus under root 7 divided by 2, right? And then you're going to do this under root s minus under root 3, s minus under root 5, s minus under root 7. Yeah, it might not be very easy for you to do the calculation because you're going to see a lot of under roots all over the places. Yeah, there might be some way for you to do the simplification, but you really know, sometimes it's not easy for you to play with this under root stuff. Even though the Heron's formula is very direct. However, it's more for some easy integer-related size, right? If you're dealing with some like very complicated side, very like nasty side, it might not be very helpful for you to do such a kind of a Heron's formula. So if that's the case, we have another way how to determine the side or like the area of a triangle. We call it the famous double Pythagorean theorem. What is that? Whenever you have A, B, C, right? Let's say A, B, C are three very nasty sides. Let's try to make a height on the third side. You're going to have this is x. This is going to be your C minus x, right? So that means that because you have two right triangles on the left, on the right, then you can actually say a squared minus x squared under root. This is going to be your height, right? Will equal to b squared minus c minus x squared, right? Which is understandable, right? There's nothing too flowery. So you would be able to solve such an equation. You can remove this under root stuff, right? This is kind of like an easy equation, and you will be able to determine the value of x. As long as you know x, you will be able to determine h, again, using the Pythagorean theorem, right? As long as you know the value of h, you can use s is equal to 1 over x, 1 over h times c. So this one looks like not so direct compared to our Heron's formula, because Heron's formula is only one big formula. It kills everything, but the calculation might be heavy. Now you break it into several parts. You do one Pythagorean theorem first. You determine the value for x, and then you do another Pythagorean theorem. You determine the value for h. So you're kind of doing first Pythagorean, second Pythagorean. You do two Pythagorean, double Pythagorean. But I think your calculation would be a lot easier than directly using this crazy Heron's formula. And this is actually the famous, what we call double Pythagorean theorem. As long as you're dealing with some weird numbers, you want to determine the height, you want to determine the area of a triangle, using the double Pythagorean theorem might be easier in terms of calculation rather than the Heron's formula. It's up to you. If you are very strong in calculation, you want to do this, that won't be in your way. But generally speaking, we recommend the second way in order to determine, the area of a given triangle. All right? So let's continue. So this is more like for our coordinate geometry. I'll just put it here as that in our coordinate, whenever we know the three sides, whenever we know the three coordinates, right? The coordinates of the three vertices, you would be able to determine the area of this triangle right away. Like I said, this is more for the coordinate geometry, but for the sake of being complete. So we're talking about how to determine the area of a triangle. I put it here. You can use the shoelace theorem directly determine the area of a triangle. And this can be more generic, not only triangle, you can determine any shape. As long as you have a polygon, so x1, y1, x2, y2, all the way, xn, yn. So you will be able to determine the area of this polygon using such a big formula. I don't think it's very helpful, to be honest. I don't think you need to remember this, but just give you a way that, we have such a formula, this shoelace formula, you get a more generic form. Instead of like doing the calculation one by one, you can use a huge formula and basically write down the area of this shape. So this is kind of like a balance, right? If you remember more formulas, you can expedite your calculation a little bit. If you do not like to remember too much formulas, you really like to calculate from scratch, it might take you more time. So it's up to you. I'll leave it to you guys. You can make a decision. You would like to remember this, or you like to do the calculation by yourself. Okay? That's the shoelace. And what about the next one? The next one is you can actually use some trigonometry to determine the area of a triangle. Let's say you have a triangle. You have two sizes, A and B, and this included angle is C. So the area is actually 1/2 A times B sine C, right? That part is, everyone knows that. You learned that from your elementary school. And the last one, and I think the last one is actually very interesting, is you can actually take some help from the circumcircle or yin circle. You will be able to determine the area of a triangle fairly quick. The first one is RS. If I have a triangle, I have a yin circle. The yin circle has a radius equals to small r. S is half of the perimeter. Half of the perimeter, this is S. So the triangle's area is going to be R times S. The yin circle's radius times half of the perimeter. Okay. And the second one is more like using the circumcircle. Whenever I have a triangle, A, B, C, and I know what is the radius of the circumcircle, you can also determine the area of the triangle fairly quick using ABC over 4R. Okay, this is actually a very shortcut way. Okay, I think one of your AIME problem actually tested. As long as you know this, you save your problem significantly. Otherwise, I think that you're going to take forever to figure out how to do the problem. But as long as you know this is going to save your time significantly, and you can get your answer fairly quick. Okay, that's actually, generally speaking, what we want to say about all the basic theorems, basic properties you need to know in order to go to the AMC12 math competition. So far, so good? Can I have some feedbacks? Are we all on the same page? Any questions? Okay, perfect. All right. So as long as we finish the first part, let's go to our second part. What are the most important typical questions you might be seeing in the AMC, in the AIME, basically in the 2D geometry parts? So I have to say, not to say something very easy peasy stuff, but generally speaking, there are 4 major parts that AMC love to test you from time to time. It's almost like more than 1 time per year. 4 major parts. What are the 4 major parts? First one is some important theorems, such as cosine law and Pythagorean theorem. Trust me, these 2 theorems are like so important. They like to test you every single year. Every year, they will basically test you cosine law, Pythagorean theorem, so many types. So as long as you see some shape, you would be able to use the cosine law, Pythagorean theorem. Always take it as your first priority. That's our first important category. Second one they like to test you so much is, just like I mentioned, the angle bisector theorem. Almost like every single year, the question is going to test you the angle bisector theorem. As long as you see an angle bisector, 95% you're going to use the angle bisector theorem. That's your first reaction, your conditional react. Always going to put it as your first option. Third one they like to test you is the similarity. But trust me, in the similarity, they barely test you, okay, the two sizes, they're proportional, blah, blah, blah. This is too naive. In AMC, the only thing they like to test you, or like the best, like the very important thing they like to test you, they're going to use such an important property. The areas ratio is actually the similarity ratio's perfect square. Right? If I have two shapes, the similarity ratio is R, for instance. The area ratio is going to be R squared. Oh, trust me, this is like so important. Every single year, they will test it. Not sometimes test in the AIME, sometimes in the AMC, sometimes in both. This is extremely important. As long as the question gives you some weird shape, blah, 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 you see any kind of similarity-related property, always try to use the similarities ratio's perfect square actually equals to the area ratio. Okay? And the fourth one they like to test you is actually circles tangency. And this part, they always give you some difficult problem. Some circle, some tangent. We already introduced what is the conditional react, right? What are you going to do whenever you see circles tangent to each other? Trust me, they always give you some challenging problems. I'm going to give you some question number 25. Sometimes looks like a crazy problem. It's kind of talking about the circles tangency. However, if you use the technology we introduced in our lecture, it's going to be so easy for you to figure them out. So these are the four major high-frequency testing problems. Some Pythagorean law, some cosine law, angle bisector theorem, similarity using the similarities ratio, perfect square equals to area ratio, and also using some complicated circle tangency problem. That's going to solve you a lot of problems. Basically, that's basically what you're going to see in the North American mass competition, especially in AMC12 and AIME. Today, we're going to give you some sample problems in this 1, 2, 3, 4 categories and give you guys some big direction. What are you going to do whenever you're dealing with all these problems? All right. So if all good, let's go to our category number 3, sample questions. We're always going to change our problem significantly for different lectures. So you're going to see this problem super different according to our previous sessions. So let's go for our first problem. Okay, our first problem, you're looking at a problem that comes from 2010. AMC12B, question number 22. So I'll give you guys maybe 30 seconds, read the problem first. And then we're going to read this problem all together and figure out how we're going to deal with such a problem. And we always give you the last 5 problems from AMC, plus some AIME problems to make sure the complexity of our lecture. Okay, let's have a look at it, how we're going to deal with such a problem. The most important thing is whenever you read it, you need to figure out what are the most important properties. First one is, let ABCD be a cyclic quadrilateral, okay? Cyclic quadrilateral. This is not a regular quadrilateral, it's a cyclic. There are some properties you need to know for cyclic quadrilateral. The sidelines of ABCD, they're distinct integers lesser than 50. Well, this is another part you need to highlight it. Normally speaking, for a quadrilateral size, there's no need to be any integer, right? You can be whatever sizes. But as long as the question gives you a special condition, there must be some reasoning, right? A quadrilateral has distinct integer lengths. There must be kind of like usage you need to know. Let's park it there, less than 50, such that BC times CD equals to AB times DA. Okay? With all those information, the question is asking for you, what is the largest possible value of BD? So as long as you see this, I think your first reaction is, let's try to give you a shape, right? So try to having a good graph is always important for any kind of geometry problems. So let's try to give a graph. So the graph, you have like A, B, C, D, four sizes. They're all like distinct integer, less than 50, whatever. And you have BC times CD equals to AB times DA. Okay. I think because we already know this is going to be a cyclic quadrilateral, right? So the first side, as long as you see such a relationship, I think people's first reaction would be using Ptolemy theorem, right? Because Ptolemy theorem is kind of like two sizes, like multiply them together equals to the two diagonals, so on and so forth. However, if you have a quick observation, you'll find out this is not exactly what Ptolemy says. Because Ptolemy says the opposite two sizes. Red, red. Green, green equals to black, black, right? This is what Ptolemy asks you to do. But this problem, they're not like opposite two sides. On the contrary, they're like adjacent two sides. So that means that maybe Ptolemy theorem might not be a very easy approach, at least not a direct approach, try to solve the problem. That's the case. Who can tell me? If you search out all those kind of theorem we talk about so far, what kind of theorem is talking about the multiple of adjacent two sizes rather than the opposite two sizes? Who can tell me? Because Ptolemy is good, right? But Ptolemy is using the opposite. Because we're not using the opposite. Like the question is not asking for like opposite. It's actually giving the adjacent. Who can tell me what kind of properties might be kind of like applicable when you're dealing with the adjacent theorems? Who can tell me? I'll be asking for maybe Hansen.
Cosine law.
Is that right? Cosine law is actually a very good way because cosine law basically using the adjacent two sizes, right? But to use cosine law, you're going to put it into a triangle. Like I said, all those kind of quadrilateral problems at the end of the day is going to go to a triangle, right? So let's try to break it into two triangles. Maybe I'm going to say this is like theta. This is going to be pi minus theta, right? Because right? If there are two, if there is like a cyclic quadrilateral, so this is going to be supplementary to each other. So one is theta, the other way is going to be cosine theta. Pi minus theta, right? This is actually something very understandable. So I'm just going to write out this cosine law thing. BD squared equals to AB squared plus AD squared minus 2AB AD cosine theta, right? That's the one for the upper triangle. Same thing, BD squared equals to BC squared plus CD squared minus 2 BC CD cosine pi minus theta, right? Very understandable. As long as you have two equations, so your goal is try to determine the value of BD, right? Don't forget where we come from. As long as you have two equations, what are you going to do? Normally speaking, adding them together, subtract one from the other, right? Like in the worst case, you might even multiply this guy together. That's pretty much what you can do. There's nothing else you can do, right? Because the question is asking you to determine the value for BD. Of course, you're going to be adding them together. You can't subtract, right? So that's going to give you 2BD squared equals to AB squared, AD squared, BC squared, CD squared, and you can find out cosine pi minus theta actually equals to minus cosine theta, right? We're using a tiny core function, not too complicated, tiny core function, cosine pi minus theta equals to cosine theta. And minus cosine theta minus 2BC, this guy is going to change into plus. And as long as you're adding these two parts together, the question already tells you what? BC times CD equals to AB times DA. AB, BC, CD. These two parts are actually equal to each other. Plus, one is negative, one is positive. So these two terms might be canceled. Right? Very understandable, right? This is not a magic. So now you're kind of having a relationship for BD. BD squared equals to what? AB squared, AD squared, BC squared, CD squared. Okay, you need to determine the largest possible value for BD squared. So what can I do? Let's go back to the question. The question says, all the 1, 2, 3, 4, the four sizes of this cyclic quadrilateral, they're distinct integers lesser than 15. So intuitively, you want to make it as big as possible. So you can make 14, 13, 12, 11. They are as big as possible, right? But can you do that? Is there something you want to do some quick tweak before you wrap up the conclusion? Can you do this? I think this is very intuitive, right? You just basically give like the three sizes. You just basically give the four sizes and then put them together. Okay, it is exactly what you need. However, before you jump to the conclusion, sometimes the question always gives you some quick tweak before you go to the final solution. I can't really randomly give 14, 13, 12, 11. Why? Because AB, AD, BC, CD, there is a relationship between them. What is the relationship? Here. BC times CD equals to AB times AD. If you just plug in 14, 13, 12, 11, this is not going to work, right? That's the only tricky part for this problem. So what you're going to do is that let's try to use as big possible, right? All the big values as big as possible. So what I can use the biggest, 14. I'm going to give BC equals 14. It doesn't matter. You can take any one to 14, doesn't matter. But think about it. As long as you have a 14 on the left-hand side, 14 equals 2 times 7. So that being said, there must be a 7 factor on the right-hand side. So AB or AD, one of them needs to be equal to 7, right? You can't get rid of it, right? 14 is on the left, 7 must be on the right. You won't be able to take whatever value you want to take. Okay, so now you're kind of like trapped. You need to find another two values on the left and on the right, and make sure this guy times 14 equals to this guy times 7, aka 2 times this guy equals to 1 times this guy. Who can tell me what is the biggest value I can put into these two brackets based on such a constraint? I want to take as big as possible, right? I can't take two smaller values. Who can tell me what are the possible biggest value I can put in order to make sure the left-hand side still works with the right-hand side. Andy Liu.
So we can put 6 on the left side and 12 on the right side.
Is it right? 6, 12. That's the biggest that I can put, right? Because you have all the numbers less than 15. That's kind of like the biggest one I can put there. There's no way I put something even bigger. So that being said, because you have such a constraint for the left-hand side, for the right-hand side, these are the 4 different segments you can basically put to make sure this relationship holds. So you can see, you can't just randomly pick up the largest 4. On the contrary, you need to pick up the ones that make sure these 2 sizes are the same. So therefore, what are you going to do? Just plug in the value. Okay, the following part is more like a calculation. This is 14, this is 6, this is 7, this is 12. You do our calculation, BD equals to root 425 divided by 2. So we have this root 425 divided by 2. You see, it's a very easy problem, right? But as long as you see these 2 things, multiply them together, these 2 things, multiply them together, your first reaction should be using the cosine law rather than using the Ptolemy theorem. This is something what I want to say in our first problem. All good? If all good, let's go to our second problem. Our second problem is a problem that comes from AIME. But again, if you understand our theorem, it's actually so easy for you to solve the problem. So this is a problem that comes from 2001, AIME 2, question number 6. Again, 30 seconds, I'll let you guys read the problem. All right, so time is up. Let's have a look at it. How are we going to rate such a problem? A square ABCD is inscribed in a circle. So the big one, like the blue one, is a square. Square EFGH, like the little one, so that's also a square. It has the vertices E and F on CD and vertices G and H on a circle. So there's basically 2 sides there, 2 vertices there, 2 vertices on a circle. And if the area of the square ABCD is 1, okay, the big square, the areas is 1. So that being said, all the sizes is 1, right? So that's basic stuff. Then the area of the square EFGH can be expressed as m over n, where m and the relatively prime numbers, m lesser than n, find a value for 10, n plus m. Like I said, this is a typical way that AIME likes to ask you. Rather than basically, ask you what's the value, because AIME needs to have a one number from 0 all the way to 999, right? So that being said, the question really want to ask you to put it into a real big number, right? Kind of like an integer number after all your calculation. So basically, the question asks you to determine what is the square, like little EFGH, what is the area of such a square? Well, if you wanted me to determine like my square's area, of course, I need to determine the side. The side of EFGH, right? As long as I go to the side, my work is done. So how can I do the side? Okay, here I'm going to teach you a very important conditional react. As long as you see a chord in a circle, a chord in a circle, more often than ever, you're going to make a perpendicular line from the circle center to the chord. This is extremely important. As long as you see a chord in a circle, always, you want to make a perpendicular line from the circle center to the chord. Why? Because let's say this is the circle center, right? As long as I'm making a perpendicular line, my perpendicular line is going to basically cut my chord into two equal parts, right? Everyone knows that. Perpendicular, let's say I have here, circle, make a perpendicular line. This is always going to cut into, this is going to be the midpoint, right? Midpoint. This part, I think everyone knows that. That's fairly easy. As long as you see this, your goal, what is your goal? Your goal is try to determine the value for EF, one of the side, and then you make a perfect square, you get what you need. In that case, maybe I'm going to let, because I already know this is going to be your mid, right? So I'm going to let this part equals to x. So my EF is going to be 2x, right? Just try to make my life a little bit easier. Okay. I know x, but how can I determine x, right? Okay, to determine x, I think the most important thing is you want to put x into a triangle, right? You need to make the relationship between your x and your 1, right? As long as you know your x, as long as you know your 1, there's any relationship, probably you get a problem solved. But how can you get a relationship? You can't really do it like something like this. You need to create a triangle in order to make sure everything can be properly handled. How can I do the triangle thing? Okay, I think this is a very, very conspicuous triangle you can help you solve the problem. I want to make the big circle, like the big square, as close to the small square as possible. I want to do something like this. I'm going to do a connection. I'm going to change the color to red from here to here. I'm going to also make another connection. So now let's try to focus in this little triangle. Okay, I'm going to give a name. Maybe I'm going to say this is P. Okay, let's focus on this very slim triangle, OPH. Let's have a look at it. How are you going to deal with such a triangle? First thing first, the triangle has a OH. OH is the radius of the circle, right? Is it easy for you to determine the radius of the circle? That's fairly easy. The question already gave you the big square actually has a length equals to 1. So if you do any kind of quick connection, this is going to be a right isosceles triangle. You have the hypotenuse equals to 1. So this is going to be 1 over root 2, which is the radius of the circle, right? So therefore, OH is also the radius, 1 over root 2. Okay, next one. What is OP? OP is easy because O is the center of the circle, aka O is also the center of your big square. So therefore, OP should be half of the square length, right? O is the center, is half of the square length. So OP will be equals to 1 over 2. Okay, they're all good. There's no x there. Everything is actually like the numbers, which is perfect. So now, how can I determine HP? Of course, I think HP, you must have some x there, right? If there's no x, so there's no way for you to do it. How can I determine HP? Determine the HP, I don't think there's a crazy problem because you can actually do your little calculation in this green triangle, right? This is the little Pythagorean theorem, right? Yes, I see many students give the correct answer. So this is going to be 2x because the EF is 2x. So EH is also 2x. So your HP is going to be root 5x, right? HP will be under root 2x squared plus x squared, which is root 5x. Okay. Now you have 3 sizes. In this very slim triangle, you have 3 sizes. As long as you see 3 sizes, I think people intuitively think about it. Maybe I'm going to do some cosine law stuff, right? 3 sizes is very nice for you to do a cosine law. Well, cosine law, let's say I'm going to say this guy equals to theta, right? I'm going to say this guy equals to theta. Let's try to do a cosine law. Cosine law is very easy. I'm going to do the OH square equals to OP square, PH square, 2OP, PH, cosine theta. Okay, I'm going to plug in the value. So OH is 1 over 2 under root perfect square. OP is 1 over 2 perfect square. PH is your 5x square and root 5x cosine theta. Now, everything looks good except this cosine theta. I have only one equation. I already have x, but I still have a cosine theta. I can't really solve this equation, right? This is like a Delphantine equation, has 2 variables. So the $1 million question is that, is it possible I can do some little trick, try to get rid of this cosine theta? And if everything works fine, can I use x to represent this cosine theta? If I can do this, my work will be perfectly done, right? So this is actually the thinking process. Every single step, there's a reasoning. You won't be able to guess out the answer right away, but every single step, you need to ask yourself what's going to happen for the next step. Now I have an equation. I have x, which is perfect, because my goal is try to determine x. But I have a cosine theta. Is there any way I can somehow convert this cosine theta into something using x? If that's the case, it's going to be like so easy. Who can tell me how I can do that? But the thinking process is very important. My goal is very clear. I'm going to replace cosine theta using x. As long as I got x, there's only one variable, my work is done. But how can I do this little trick to convert it into x? Let's think about it. I'm going to highlight it from here. The cosine, like this theta is actually obtuse triangle, right? The theta is like this obtuse angle. So this angle actually contains 2 parts. One is a 90 degree. The other part is here, right? This is 90 degree. I don't really care, right? And this is here. So if that's the case, I'm going to ask maybe Eric. Eric, yeah. Okay, can you tell me what do you think for such a problem?
Like HP. Oh, I mean, theta includes the 90-degree angle and EPH, and we already know cosine EPH, so we know theta, cosine theta.
Is that right? Yes, I think Eric's explanation is a little bit faster, but that's exactly what's going to happen. I'm not so sure how to do cosine theta, but I can use some very tiny core function. Cosine theta equals to what? Equals to sine 90 degrees minus theta. A little bit tiny core function. And this 90 degrees minus theta actually equals to minus sine theta minus 90 degrees. Is that right? minus sine theta minus 90 degrees. Where is my theta minus 90 degrees? It's exactly this little yellow stuff. This is going to be my theta minus 90 degrees. So that being said, if I drag it out, that's going to be something like this. This is your theta minus 90 degrees. This is your 2x. This is your x. This is your root 5x. So now, do you know how to determine this? Of course, because your minus theta sine theta minus 90 degrees is exactly in this triangle, this right triangle, using 2x over root 5x. Is it right? Voila. In that case, you successfully replace cosine theta using not even x, right? Using a constant because the x might be canceled. Now you're dealing with only a triangle, only an equation with one variable, aka only x. Solve the equation, you'll be able to get a value of x, which is 1 over 10. And taken from there, you'll be able to determine the area of the small EFGH, which should be 2x squared, right? Don't forget, x is only half of the EF, 2x squared. So that one is going to give you 1 over 25. And the question is asked you, this one is actually equals to m over n. So 10m plus n equals to 250, 10m plus m, excuse me, 10m plus m equals to 251. You see, this is a very linear thinking process, right? You're not doing something too crazy, too complicated, but as long as you follow this linear thinking process, you will be able to get what you need fairly quick, right? So these two problems, I think is good enough for you to say, as long as you'll be able to get a cosine law, you'll be able to get a Pythagorean theorem, try to use it. That's going to help you to expedite your calculation process significantly. So far, so good? Perfect? If all good, let's go to our second category. Our second category, let's try to talk about some angle bisector related stuff. Like I said, angle bisector theorem is like so important. They will test you from time to time in any kind of math competition. Let's go for one AMC problem first. Okay. Again, 30 seconds, I'll let you guys read it. That's a problem from 2013, AMC12B, question number 24. Okay, let's have a look at it. The question says, let ABCD be a triangle where M is the midpoint of AC. M is the midpoint, okay? And CN is the angle bisector of angle ACB. These two parts, angle bisector. Like I said, as long as you say angle bisector, most likely you're going to be using your angle bisector theorem. But let's wait for a sec. And let X be the intersection between the median BM and the bisector CN. And additionally, angle triangle BXN is an equilateral triangle. Sorry about my writing. Like my graph is horrible, but you can do some imagination. This is actually a equilateral triangle. Okay, equilateral means what? They're all 60 degrees, right? 60, 60, 60. Okay, and with AC equals to 2. Because M is the mid, right? So this is 1, this is 1. With all those information, the question asks you to determine the value for bx squared. Bx squared. Well, to determine the value for bx squared, you basically need to determine, because like the little red triangle is equilateral triangle, so bx, bn, and x, everything is good, right? As long as you determine 1, we're good to go. How can I deal with such a problem? This is a little bit challenging because this is kind of like something flying there, right? I need to make the relationship between all this kind of size in order to determine what's the value for bx or bn. If that's the case, let's do some quick analysis before we get started. First thing first, as long as you know the angle bisector, you're pretty much going to do this angle bisector theorem. We're going to park it from there for a second. Before we jump to the angle bisector theorem, because you have a equilateral triangle means it's 60 degrees all over the places, we might be able to do some angle chasing. Let's say I'm going to call this is angle X, okay? Angle X. So here you can find out this guy is 60 degrees. So 60 degrees equals to, I'm going to use this color, 60 degrees equals to x plus dot. Is it right? Because this is the external angle equals to the sum of the two not adjacent internal angle. 60 degrees equals to x plus dot. And also, I have this. This is also 60 degrees, also equals to angle A plus dot. Is it right? Angle A plus angle dot. These are also considered to be the external angle for angle X. So that being said, you have angle A plus dot equals to angle X equal dot. Therefore, angle A equals to angle X, right? I'm going to say this is also X. You guys follow me? Yes or no? Can I have some feedbacks? Are we on the same page? Fairly understandable, right? So the external angle, like the outside angle is the external angles to sum. As long as you see this, if you follow our regular lecture, we actually introduced there are 10 different ways to find your similar triangle. You automatically find out these two triangles. I'm going to change the color to green. These two triangles, the green triangle and the biggest triangle ABC, they're actually similar to each other. Is it right? We have introduced in our lecture, as long as you have something like this angle equals to this angle, so therefore automatically your red triangle will be similar to the biggest triangle ABC. Is it right? This is actually our conditional react. You need to remember all the conditional react we introduced. You can't really think for every single problem, like I said. You need to basically use the conditional react to solve the problem. Okay, if that's the case, as long as, I'm just going to write it here, triangle BMC is actually similar to triangle ABC. BMC is the green one, triangle ABC is the big one. As long as you have the similarity, you have the proportional relationship. BC over MC, AC over BC, aka BC squared equals to AC times MC. Is that right? Every single step, there's a reason, there's a conditional react. As long as you do this, what's going to happen? You will be able to get a value of BC. BC will be equals to √2, right? This is going to be your √2. Okay? Okay. As long as I get my BC is √2, I'm kind of okay, ready for my angle bisector. Why? Because like I said, don't forget your angle bisector. Angle bisector is going to be the most important thing in this problem. You have to use it. There's going to be no way around. It's time to use the angle bisector. In this problem, I said this guy is the angle bisector, right? But this guy actually contains two triangles. One is the green triangle, like I highlighted here. The other one is the big triangle ABC. So maybe you have to use the angle bisector twice, in order to make it work. In triangle BMC, I'm going to have BC over MC equals to BX over XM. BC over MC, BX over XM, right? BC is √2, MC is 1. So basically, BX over XM is √2 over 1. Right? Easy peasy. Same thing in triangle ABC. I'm going to do exactly the same thing. BC over AC equals to BN over NA, which is also equals to, let me change a different color, help you guys to understand. BC is here over AC equals to BN over NA. This is √2 over 2. Don't forget, BX, BN, they are the two sizes of this equilateral triangle. Right? They are the same. So that being said, actually means what? Actually means this two yellow segments and my two black segments, they're all proportional to each other, right? You can actually use one variable to present them all. Why? Because from here, BX is √2 of XM. I'm going to let XM equals to A to make my life easier. This is A. Then your BX will be √2 times A, right? If BX is √2 times A, BX and BN, they're the two sides of an equilateral triangle. This is the same, √2 times A. As long as you know √2 times A and A, here, this is going to be 2A. Is it right? So far, so good? Can I have some feedbacks? Are we all good? Now we're actually using one variable and we represent all the segments. That's so nice, right? Okay, now what is my goal? Where did it come from? My goal is try to determine what's the value for Bx. What's the value for Bx? Now Bx is actually, in our case, is the yellow one, right? It's under √A, under √2A. So that being said, as long as I can find one equation, because for now, this triangle, they're all A's, right? Either A's or segment I know. As long as I know one equation, my work is done. So now, for you guys, who can tell me what is the equation I can construct using such a formula, such a shape? Who can tell me? I just need one equation. This equation just have one variable A, and my work is done. How can I get this equation? and taking from there, figure out the solution. I see student got answer. I'm going to be asking maybe Alex. Like, yes, you go ahead.
The cosine law on ABM, because like you know all the sides and like you know an angle stuff.
Is that right? That's a brilliant answer. Because for now, you know what? You can just use the cosine law in such a triangle. I'm going to, in this triangle, you already know that the top angle is equals to 60 degrees. And all the other angles, you can create them using A or under root A, blah, 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 like under root 2A, blah, blah, blah. Everything is there, right? Like I said, cosine law is like so important. You're going to use it all over the places. That's a brilliant answer. So I'm going to do my little triangle A, B, M, because one side is going to be 2 plus root 2, A. This guy is going to be root 2 plus 1A. This guy is going to be 1, and this is your 60 degrees. So you just basically use a cosine law in triangle ABM, and you're going to be able to have a big equation for A, right? I'm not going to write an equation. It's like the big equation for A. So that one equals to cosine 60 degrees. Taking from there, you get a value for A. And then the question asks you to determine what's the value for bx squared. Bx squared is under root 2a perfect square. So 2a squared. That's going to be 10 minus 6 root 2 under root 7, over 7. Do we have it? That's going to be our A part. You see, such a problem. We're not using something too crazy, something too complicated, but as long as you know the angle bisector theorem, you know the cosine law, you'll be able to solve it. And this is considered to be a relatively difficult geometry problem in our AMC. It's question number 24. Okay, so using this kind of conditional react is going to be very helpful when you're dealing with all those kind of geometry related problems. So far, so good. I think for this part, it's actually very mechanical, right? You see the angle bisector, you use the angle bisector theorem, you solve the problem, and voila, that's it. So I don't think we're going to use too much samples. One sample is good enough. You just remember, always use the angle bisector theorem, and you are good to go. All right? If all good, let's go to our category number 3. Let's talk about another very important topic, similarity. Like I said, they won't really ask you to do some similarities, proving something, so on and so forth. Not too many, but they might use the similarities perfect square as actually areas ratio. That's going to be something very important. Okay, if you're good, let's go for one sample problem. Let's go for one AIME problem. 3. Okay, let's go for this AIME problem. It's a problem that comes from 2010 AIME 2, question number 9. Again, 30 seconds. Please read the problem. Okay, so let's have a look at it all together. Let ABCD is a regular hexagon, okay? And let my G, H, I, J, K, L, they are the midpoint of the 6 sizes, okay? So you have a regular hexagon, you find all the sizes, and then you make the connection, okay? You connect all the things, okay? So after you do the connection, you can find out you're going to be able to boundary out a little regular hexagon in the middle, which makes sense, right? I'm just going to highlight it using here. So like the middle one is also a regular hexagon. Okay. And then the question says, let a ratio of the area of the smaller hexagon to the area of the big hexagon can be expressed as the fragment m over n, where m and the relative prime numbers, find a value for m plus n. Like I said, these are typical way that AIME asks you a question. So long story short, you need to find out the area ratio. The smaller one, big one, area ratio. Okay, this is very understandable. You get a big regular hexagon and you get a small regular hexagon. You want to determine what is the area ratio. Well, like I said, if you just want to determine the area of a hexagon, that's going to take you some time, right? You're going to do some calculations, so on and so forth. But these two hexagons, for sure, they are similar to each other, right? That's for sure. The smaller one, the big one, they must be similar to each other. So if I can do some magic, I can find out the similar ratio between these two shapes, then I would probably solve the problem fairly quick. Is that right? So as long as I got a similar ratio and make a perfect score, I'll be able to see the area ratio between the smaller one and the big one. But the million-dollar question is, how can I find out the similar ratio between the two? Intuitively, you want to do the side, right? AB, AF, right? And then you'll find the little one in the middle. Well, the most challenging part is these kind of, I'm going to change the color to blue. This is my blue one, right? And this is my black one. The black one is okay, but the blue one is right flying there in the middle. It's very, very difficult for me to determine what is the blue one, what is the red one, right? Like the black one is okay. I can just make a value, it doesn't matter. But the blue one is like flying there. It's kind of like difficult for us to find a relationship. Because whenever we want to determine you, we must put it into a triangle. This is what I keep saying from day one. But how can I put it into a triangle? This is a little bit challenging. So if that's the case, we're going to be a little bit alternative. You not always stick to one segment. You want to do some quick tweak before you can make it happen. This time, I'm no longer stick to this side, like the blue one or the black one. I'm going to do a magic thing from here. But I think this is going to be very understandable as well. I'm going to find out the center. I'm just going to give me one sec. Okay. I'm going to find out the center of the shape. From the center of the shape, I'm going to make a perpendicular line to this blue line. I'm going to do a connection between OH, let's say a given name, OH. So that being said, let's have a quick discussion. This is going to be, my OH is going to be definitely perpendicular to BC, right? Because BCH is the midpoint. So OH is perpendicular to BC. Same thing, if this is a given name, maybe M, for instance. So my OM is also going to be perpendicular to AH, right? This is 90 degree. OH perpendicular to BC. This is also 90 degree. So that being said, it's kind of like consider the distance between the middle, the center, to one of the height, to one of the sides. if I can find out the value for OH over OM, I'm also kind of determining this is the similarity ratio. Is it right? Similarity ratio. OH over OM. Because OH is from the big regular hexagon, from the middle all the way to one of the sides. And OM is from the smaller one from the middle all the way to one of the sides. These two ratios will still be giving you guys exactly what you need. Do you guys follow me? Yes or no? Yes or no? Perfect, right? Okay. Let's try to determine the one of the other. Let's say it is possible or not. For OH, I think for OH, that's easy. OH, I'm going to do any kind of, do a connection here, do a connection here, do a connection here. Let's say I want to say for the outer regular hexagon, the size is 2. So this is 1, right? Just want to make my life easier. So OH is going to be equals to OJ, right? That's the height. So that one should be fairly easy. √3. That one, everyone knows that you have a equilateral triangle, right? How to determine equilateral triangle's height. That one is too easy. For the equilateral triangle, the height is actually √3 over 2 times A, right? Everyone knows that. So OH, this is √3. Very easy. But the difficult part is, how can I determine OM? How can I determine OM? This is a little bit challenging. And that's the part we can use some little trick. I'm going to do a connection between OA. Now, I'm going to focus in this blue triangle. I'm going to focus in this blue triangle. Okay. In this blue triangle, I have already determined the value for OH, which is √3. I know the value for OA. OA is 2, right? OA is more like the side, right? So if in a triangle, in this blue triangle, I already know OA, I already know OH, how can I determine OM? Actually, if I can do some magic and figure out what's the value for, change the color to here, AH. If I know OAH, I would be able to determine OM. Is that right? This is exactly what we mentioned. In a triangle, you know this guy, you know this guy, you know this guy. You can use the double Pythagorean theorem. You will be able to determine what is the height of OM. Is it right? This is exactly what we mentioned. Double Pythagorean theorem. You know the three sizes, it's very easy for you to determine the height. So the $1 million question is, how can I determine AH? Who can tell me? How can I determine AH? I'll be asking for Paul.
You just use the cosine law on triangle ABH.
Is that right? That's a brilliant answer. You see, after all these questions, we're still going to use the cosine law. Cosine law is our lifesaver, right? We always use the cosine law. We're going to use the cosine law in this yellow triangle. Why? Because here is 120 degrees. This is, you told me this is 2. This is 1. So AH is very easy for you to determine. AH would be √7. Still, I'm going to be using the cosine. Like I said, cosine is like so important. And that's the reason that's the first theorem I gave you guys, right? Number one important thing, because no matter you go to AME, AMC, whatever places, cosine law is the most important thing. You're going to use it every single day. So that being said, as long as you use the cosine law, you'll be able to get AH. As long as you get AH, using the double Pythagorean theorem, you'll be able to get OM. I'm going to tell you the value for OM. OM is a nasty number, under root 12 over 7. As long as you know the OM over AH, that's going to be your similarities ratio. And the area ratio will be the similarity ratios per fixed square. In our case, 4 over 7. So m plus n is going to be equals to 11. You see? Very understandable. Okay. A student got a question. AOH is the right triangle. I don't really know, to be honest. Yeah, maybe you figured it out later, but I don't really know because I'm using the double Pythagorean theorem. I don't really care if it's a right triangle or it's not a right triangle. It might be a right triangle, right? No problem. But you can always use the double Pythagorean theorem in order to make it work. Is that right? Any questions? So far, so good? Okay, perfect. Yeah, any questions, just let me know. Okay? Yeah, I don't really care it's a right triangle or it's not right triangle. I don't really care because the double Pythagorean theorem can solve all the problems for me regardless it's a right triangle or it's a like acute triangle or something. I don't really care. It might be a right triangle, I don't know. But yeah, in this case, it is a right triangle. But yeah, it just happened to be a triangle. I've not really relied on a right triangle to make it work. Right? Perfect. Okay, let's go to, okay, that's also one sample problem is good enough. Let's go to our last problem. Sorry, it's our first lecture. We have some like introduction, something, so we might run out of time a little bit, but normally speaking, our lecture is only 2 hours. Okay, it's our first lecture, might be a little bit longer. So let's go to our last category. Our last category is more like number 4. It's more like some complicated problems when you're reading the circle tangent. Circle tangent. You might see a lot of crazy problems, but trust me, as long as you see those problems, follow what we introduced in our lecture of our common strategies, conditional react, you will be able to solve the problem fairly understandable. Let's go for one crazy problem. I think this is one of the most crazy problem you can see from AMC. A lot of people just get scared when you see the problem. But trust me, no need. As long as you follow what we introduced in our lecture, this is something so understandable. We're looking at a problem that comes from 2015, AMC12-A, question number 25. I'll let you guys read the problem first. This is a crazy problem, I have to say. But the solution process is very understandable. All right, let's have a look at this problem altogether. The problem says a collection of circles in the upper half plane, all tangent to the x-axis, is constructed in layers as follows. They basically go for different layers. Layer L0 consists 2 circles of really 70 square and 73 square. Oh my God, why did I give you something so nasty? 70 square, 73 square. There must be some reasoning. Let's just park it there. They are externally tangent. For k greater or equal to 1, the circles in such a joint union LJ, they're ordered according to the points of tangency with the x-axis. For every pair of consecutive circles in this order, a new circle is constructed externally tangent to each of the two circles in the pair. Layer LK consists of 2 to the power of k minus 1 circles constructed in such a way. And let S equals to J equals to 0 to 6 LJ, basically L1, L2, all the way to L0, L1, L2, all the way to L6. For every circle denoted by RC in this radius, and the question asks you such a nasty relationship. I think most of the students do not really understand what the question is asking for you. That's the challenging part of this problem. So this problem actually asking for what? It just basically said, you have a bunch of circles. They are externally tangent to each other, okay? At the very, very beginning, you have two circles. One is 72 square with the radius. One is a 70 square. Okay, I think like the 70 should be this. 70 square. The other one is a 73 square. Okay, this is your layer 0. From layer 1, you do such a thing. You always want to make a new circle which is tangent to the upper layer circle. So this is your layer 1. I'm going to use your 1, okay? This is your number 1 circle. Okay, you tangent to this 2 layer 0 circle, right? And then moving forward, you can go to your layer 2 circle. Layer 2 circle is these two circles. It basically tangent to the upper layer, because for the left, layer 2 is actually tangent to the 73 square and the layer 1 circle, right? To the right is the layer 1 circle and the 70. Okay? As long as you're done for the layer 2, let's go for layer 3. Layer 3 is the same thing. It's actually this guy. It is actually tangent to the 73 square circle and the layer 2. The other one is here. It's tangent to the layer 2 circle, layer 1. The third one is here, tangent to layer 1, layer 2. And the other third one is here, tangent to layer 2 and 72 square. Okay? So this is actually what the question is asking for you. And then what the question says, you need to find out all those kind of circles radius, and then doing such a 1 over under root stuff together, adding everything together. Layer 0, layer 1, layer 2, all the way to layer 6. You see, like the more you write, so the other one is going to be 4, right? And 4, 4, 4, 4, 4, 4, 4, right? You just keep writing more and more and more and more for all this kind of stuff. Each layer, the circle number will be exponentially increased into 2 to the power of k minus 1. Because whenever k equals to 1 is 2 to the power of 0, there's only one layer, only one circle. K equals to 2 to the power of 1, you have 2 circles. K equals to 3, 2 square, you have 1, 2, 3, 4, 4 circles, so on and so forth. Okay? The question is asking, what about I put all those circles together, I calculate their, what should I say, their radius, right? I do reciprocal, put everything together. How can I deal with all those kind of weird things? So trust me, even though you're dealing with a weird problem, you always want to go what we introduced in our lecture. We have mentioned, as long as you have 2 circles tangent to each other, as long as you see there's a common tangent line, in our case, it's the x-axis, what are you going to do? Still remember? Big one, small one. We always want to do this, connection, perpendicular line. All the magic is going to happen from here, right? This is big R minus small r. big R plus small r. This is 2 root big R times small r. Is that right? We're going to use exactly the same thing, help you to solve the problem. Okay, let's have a quick look at it. Your goal is try to determine all the layers, all the circles, right? So let's get started. Don't ask for too much. Let's go to 1 layer, 2 layer, right? Hopefully we got a pattern, and then hopefully we solved all the problem as is. So what we're going to do, we're going to do something like this. We're going to follow what we introduced in our lecture. We're going to make all those auxiliary lines. First thing first, I'm going to do a connection from the circle center all the way to the perpendicular line, right? I'm going to make a connection from the circle center all the way to this tangent line. I'm going to connect them together, right? And then, like I said, these guys will basically collinear with the tangent point. And I'm going to be making such a perpendicular line in order to basically to construct this little triangle, right? This is exactly what we mentioned. Nothing too complicated. Okay, now I'm going to let the left-hand side, this is x. Okay, the radius is x. I know one is 73, one is 70 square, right? I don't really care, but I'm just gonna put it x. I'm gonna say this is y. This is y. So according to, I'm gonna say this is c. According to what we mentioned, like I said, all the magic happens in this little slim right triangle. The c value will be equals to 2 under root x times y. Is it right? This is what we introduced here. C equals to root 2 under root x times y. This is understandable, right? This is our conditional react. This is more like for layer 0, it doesn't really tell too much, right? Let's talk something about our layer 1. Layer 1 is here. According to what we're going to do, exactly the same thing. What should I say? 2 circles, they are tangent to each other. What are you going to do? Change the color, do a connection between circle centers, right? Do a connection between circle centers. And then I'm going to do the connection between my circle center all the way to the tangent line. Everything is according to our strategy. And then I'm going to make a perpendicular line to here. Everything is exactly what we need. If I give a name, this is Z. The new circle in the first layer is Z. So this is going to be Z as well, right? Now let's have a quick look at it. This specific triangle. This black triangle. In this black triangle, you can tell me if this is A, this is going to be my Y plus Z. This is going to be my Y minus Z, right? So in this black triangle, this is A, Y plus Z, Y minus Z. We would be able to use in the Pythagorean theorem. Like I said, Pythagorean theorem is all over the places. Y plus Z square, A square, Y minus Z square. So A is going to be equals to 2 root Y times Z. You guys follow me? Yes or no? Can I have some feedbacks? Are we good? A equals to 2 under root Y times Z. You can use the Pythagorean theorem. There's nothing too flowery, right? Okay. But this is only for the left-hand side, right? This is only for the right-hand side. Can we do the same thing for the right-hand side? I think yes, we could. I'm going to change color maybe to green. Exactly the same thing. In this green triangle, you're going to have this is x plus z. This is x minus z. This is, let me say, b. X plus z. This is your z. X minus z. This is your b, right? Same thing. Same thing for the left. Same thing for the right. You're going to have x plus z perfect square. X minus z perfect square b square. So b equals to 2 root xy. Xz, excuse me. Is that right? Very understandable. Now, let's have a look at it. This is your B. This is your A. And they're adding together actually equals to C, right? You do not have too much segments. There are only 1 or 2 segments you can do. So A plus B equals to C. 2 root yz, 2 root xz equals to 2 root xy. You know what? You do a quick analysis, quick simplification, you get 1 over root z equals to 1 over root x plus 1 over root y. Oh, now you understand. Okay, as long as you want me to determine this layer, x, z's radius, I just have to use the attached, your tangent to 2 circles, right? You just use these 2 circles under root reciprocal. It's going to be equal to my radius. Is that right? So my radius z is going to be equal to, because I'm going to be tangent to only 2 circles, my radius is going to be determined solely by the reciprocals under root or under root reciprocal of my touching 2 circles. That's going to be my radius. Is that right? Oh, it's like so easy. And that's actually explain why the question asks you such a nasty form, because everything will be under root, and then take a reciprocal form. Right? As long as you know how to determine the first layer for one, you're going to do the same thing for the second layer. But this guy is going to be the reciprocal under root of this guy and this guy. The reciprocal under root, this guy, this guy. And then you can do exactly the same thing for the third. Reciprocal this guy, this guy. 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 You see, there is a pattern for it. Right? This is the pattern for it. So how are we going to do? Let's do this. You wanted me to ask all the layer from layer 0 all the way to layer 6, right? So my layer 1, so my layer 0. My layer 0 is actually the under root reciprocal of this 37 square and 30 square. This is given by the problem. So my arrow 0 will be 1 over 37, 1 over 30, 1 over 70, 1 over 73. Right? It's the reciprocal and then take an under root. What my layer 1? My layer 1 is exactly here, touching this guy, touching this guy. I only want to take the reciprocal sum. So this is also, this guy is actually equal to layer 0. What about my layer 2? My layer 2 will be 73, take a reciprocal, plus z, take a reciprocal. Z take a reciprocal plus 70, take a reciprocal. Right? 1 over under root z. Don't forget, oops. This is exactly 2 layer 0 plus 0 is actually 3 layer 0. Is that right? Very understandable. And then what about my layer 3? Layer 3 will be, like I said, layer 3. Layer 3 will be layer 0, layer 2. Layer 2, layer 1. Layer 1, layer 2. Layer 2, layer 1. Right? So that's going to be 1 over R0, 1 over R2, 1 over R2, 1 over R1. And we want to take multiple 2 because the two sides are actually symmetric. You know one side, you know the other side. Right? Very understandable. This is going to be what? This is going to be what? 9 layer 0. You know what? If you do not really 100% sure, you can write the layer 4 again one more time. This is going to be 27 layer 0. Your goal is try to add first one, second one, ninth one, 27th one. That's going to be 1 plus 3, 3 squared all the way, 3 to the power of k all together. That's going to give you 3 to the power of k plus 1 minus 1, 2. Okay, you plug in the value for the k. K is actually equal to 6, right? So you get what you need. So this is actually this guy. You see, this problem looks like a little bit challenging, but actually, if you really scratch the surface, dig into the essence of this problem, you're going to find out this one is actually basically using what we introduced. As long as you see two circles tangent to each other, use whatever we introduced here. I'm going to change the color maybe to here, to yellow. This is the first time you use it. And then the second time, the third time, and then you find out, okay, there's such a nice relationship between the two circles. And this is what you're going to do for such a problem. Okay, this problem might be a little bit challenging, but the overall flow is very understandable. Using whatever we introduce in our lecture, you will be able to solve the problem fairly quick. All right, that's actually our first lecture. I know we're actually running out of some time because first lecture is always going to be a lot of things to do. So hopefully you guys have a rough idea what is our lecture looks like. We're going to give you guys all the knowledge base. We're going to give you guys the most important problems. And then the most important things, we're going to give you some problems from AMC, from AIME, try to help you guys understand how to basically do such a problem. So hopefully today's lecture can give you some heads up. And you can basically use the technology we introduced in our lecture, and we'll be able to help you guys out in the upcoming AMC 12 and AIME exams. If you want some free lectures, we have a lot of sample lectures for you guys. You can scan this barcode, and you can take a screenshot for this barcode, and our assistant is going to help you to give you guys all those kind of free lectures. All right, that's pretty much what I want to say for today's lecture. You have any questions for me? All good? No questions? Okay. In that case, I wish you guys enjoyed today's lecture, and I wish you guys a good long weekend. Bye, guys.